Unconventional machining process. Course code U18Peme033. Topic Introduction to Unconventional Machining Process. Lecture delivered by P.P.Durairaj, Assistant Professor, Department of Mechanical Engineering, Bharat Institute of Higher Education and Research. His subject is Unconventional Machining Process, and this syllabus is Introduction, Need for Non-Traditional Machining Methods, Classification of Modern Machining Processes, Consideration in Process Selection, Materials, Conventional and versus Unconventional Machining Process, Applications, Parameters, Economics Considerations, Application and Limitations. Introduction. The unconventional methods of machining have several specific advantages over conventional methods of machining, and this promise formidable task to be undertaken and set a new record in the manufacturing technology. These methods are not limited by hardness, toughness, and brittleness of materials and can produce any intricate shape on any workpiece material by suitable control over the various physical parameters of the processes. However, unconventional methods are not suitable for conventional machining methods but are only complementing them. The new technological processes can be classified into various groups according to type of energy required to shape materials: mechanical, thermal, and electrothermal, or chemical or electrochemical. Basic mechanism involved in the process: erosion, ionic dissolution, vaporization. Source of energy required for material removal: hydrostatic pressure, high current density, high voltage, ionized material. Finally, medium of transfer of these energies: high velocity particles, electrolyte, electron, hot gases. The unconventional machining process do not employ a conventional or traditional tool for metal removal. Instead, they directly utilize some form of energy for metal machining. In this process, there is no direct physical contact between the tool and the workpiece. Therefore, the tool material need not be harder than the workpiece material as in conventional machining. The conventional forming processes, the metals are formed through the release and application of large amounts of energy in a very short time. Demerits of conventional machining process. In conventional machining, metal is removed by chip formation, which is an expensive and difficult process. Chips produced during this process are unwanted byproducts. Removal of these chips and their disposal and recycling is a very tedious procedure involving energy and money. Very large cutting forces are involved in this process. So, proper holding of workpiece is most important. Due to large cutting forces and large amount of heat generated between the tool and workpiece interface, undesirable deformation and residual stresses are developed in the workpiece. It is not possible to produce chips by conventional machining process for delicate components like semiconductors. Needs for unconventional machining processes. The harder and difficult to machine materials such as carbides, stainless steel, nitrile, and many other high strength temperature resistant alloys find wide application in aerospace and nuclear engineering industries. Many of these materials also find applications in other industries owing to their high strength to weight ratio, hardness, and heat resisting qualities. Needs for such materials, the conventional edge tool machining is high and economical, and the degree of accuracy and surface finish attainable are poor. The conventional machining processes have been deployed to overcome all these difficulties. Unconventional machining processes can be divided into following two categories. First one is unconventional machining processes or non-traditional machining processes. Second, unconventional forming processes. Unconventional machining processes. The unconventional machining processes do not employ a conventional or traditional tool for metal removal. Instead, they directly utilize some form of energy for metal machining. In this process, there is no direct physical contact between the tool and workpiece. Therefore, the tool material need not be harder than the workpiece material as in conventional machining. In unconventional forming processes, the metals are formed through the release and application of large amount of energy in a very short time interval. Classifications. The new technological processes can be classified into various groups according to A. Type of energy required to shape materials: mechanical, thermal, and electrothermal, or chemical and electrochemical. B. Basic mechanism involved in the processes: erosion, ionic dissolution, vaporization. C. Source of energy required for material removal: hydrostatic pressure, high current density, high voltage, ionized material. The medium for transfer of these energies: high velocity particles, electrolyte, electron, hot gases. Thermal energy methods. In these methods, heat energy is concentrated on a small area of the workpiece to melt and vaporize the tiny bits of work material. The required shape is obtained by the continued repetition of this process. Thermal energy method examples: laser beam machining, plasma arc machining, electron beam machining, ion beam machining, hot machining. Second one, electrical energy methods. In these methods, electrical energy is directly used to cut the material to get the final shape and size. Examples: electro discharge machining, wire cut electrical discharge machining, electro hydraulic forming, magnetic pulse forming. Third one is electrochemical energy methods. In these methods, material is removed by ion displacement of workpiece materials in contact with the chemical solution. Examples: electrochemical machining, electrochemical grinding, electrochemical honing, electrochemical deburring, explosive fabrication, that means high energy rate forming. Chemical energy methods. These methods involve controlled etching of the workpiece material in contact with a chemical solution. Example: chemical machining. Mechanical energy methods. In mechanical energy methods, the material is removed by mechanical erosion of the workpiece material. Examples: ultrasonic machining, abrasive jet machining, water jet machining, high velocity forming. All methods are not suitable for all materials. Depending on the material to be machined, following methods can be used as shown in the table. Now, the material, as per the material, the non-metals like ceramics, plastics, and glass, ultrasonic machining, abrasive jet machining, electron beam machining, laser beam machining, these are all can be done. Refractories used by ultrasonic machining, abrasive jet machining, electronic discharge machining, electron beam machining. Titanium materials can be used by EDM. Superalloys can be used by AJM, ECM, EDM, PAM. Steel by ECM, CHM, EDM, PAM. Process selection. In order to make use of non-traditional machining processes efficiently, it is necessary to know the exact nature of machine problem. The following points must be considered for the correct selection of unconventional machining processes. Physical parameters, shapes to be machined, process capability or machine characteristics, economic consideration. Physical parameters. The various physical parameters of different unconventional machining processes are given as follows: potential, power, medium, current, gap per millimeter, work material. Shapes to be machined. The application of the unconventional machining process is also influenced by the shape and size of the workpiece to be produced. Small micro holes, LBM, small holes, EVM, deep holes, ECM, shallow holes, USM and EDM, precision through cavities, UCM or EDM, honing, ECM, etching small portions, ECM or EDM, grinding, AJM or EDM, deburring, USM and or AJM, threading, EDM, clean rapid cuts and profiles, EAM, shallow packeting, AJM. Process capability. The machining characteristics or process capability can be analyzed with respect to metal removal rate obtained, tolerance maintained, surface finish obtained, depth of surface penetration, power required for machining. Process economy. The economics of the various processes are analyzed by considering the following points: capital cost, tooling cost, power requirements, metal removal rate efficiency, tool consumption. Limitations. Unconventional machining processes are more expensive, metal removal rate is slow, AJM, CHM, EAM, and EBM are not commercially economical processes. Advantages. It increases productivity, it reduces number of rejected components, close tolerance is possible, the tool material need not be harder than workpiece material, harder and difficult machine materials can be machined by this process. The machined surface do not have any residual stresses. Abrasive jet machining, water jet machining, abrasive water jet machining, ultrasonic machining. These are all the mechanical based, mechanical energy based machining. This what we are going to study for this work principles, the equipment used, process parameters, and the material rate of material removed rate applications. These are all we are going to study for this further. First, abrasive jet machining. Abrasive jet machining is the process of impinging the high-speed stream of abrasive particles by high-pressure gas or air on the work surface through a nozzle, and metal removal occurs due to aeration caused by high-speed abrasive particles. This is the schematic drawing for abrasive jet machining. See here, gas or water supply through the power supply and mixer, and there is a through hose, it is through the hand holder, and through a nozzle that mixture of abrasive and the water is forcefully fed to the surface on the surface of the workpiece. Then what happened? There is a erosion. Through the erosion, material is removed. Construction and working of abrasive jet machine. It consists of mixing chamber, a gas filter, pressure gas regulator, and the nozzle. The filter gas at pressure of 2 to 8 kgf per centimeter square is supplied to the mixing chamber containing the abrasive powder and vibrating at 50 Hz, where it mixes with abrasive particles and then enters into the connective hose. The abrasive and the gas mixture comes out from the nozzle at a high velocity ranging from 150 to 300 meters per minute and impinges over the work surface, causing abrasion action by repeated impacts, and the material is removed by the erosion. Abrasive power feed rate can be controlled by the amplitude of vibration of mixing chamber. A pressure regulator controls the gas flow and pressure. Construction and working abrasive jet machine. Control the size and shape of the cut. Either workpiece or nozzle is moved by cams, pantographs, or an other suitable mechanism. The carrier gas should be cheap and non-toxic and easily available. It is generally air or nitrogen. Abrasives generally used are aluminum oxide, silicon carbide, or glass powder. The nozzle is generally made by harder materials such as ceramic or tungsten carbide to reduce abrasion wear. The material removal rate depends on the diameter of the nozzle, jet pressure, composition of mixers, hardness of abrasive particles, and workpiece, particle size, the velocity of jet, and the distance between work and nozzle. Metal removal rate process parameters. The metal removal rate depends upon the following parameters: mass flow rate, abrasive grain size, gas pressure, velocity of abrasive particles, max mixing ratio, nozzle tip clearance. Mass flow rate. At particular pressure, the material removal rate increases with the abrasive flow rate. But after reaching an optimum value, the material removal rate decreases with a further increase in abrasive flow rate. This is due to the fact that the flow rate of gas or air decreases with the increase of abrasive flow rate. Abrasive grain size. The various abrasive particles used in AJM process are aluminum oxide, silicon carbide, glass powder, dolomite, and specially prepared sodium bicarbonate. Aluminum oxide is a general purpose abrasive and is used in sizes of 10, 25, and 50 microns. Silicon carbide is used for faster cutting on extremely hard materials. It is used in sizes of 25 to and 50 microns. Dolomite of 200 grit size is found suitable for lighter cleaning and etching. Glass powder of 0.30 to 0.60 mm are used for light polishing and deburring. In general, large sizes are used for rapid removal rate, while smaller sizes are used for good surface finish and precision. Gas pressure. The metal removal rate increases with increase in gas or air pressure in direct proportional. Velocity of abrasive particles. The metal removal rate increases with the increase of velocity of abrasive particles in direct proportional. Mixing ratio. Mixing ratio is defined as a ratio of mass flow rate of abrasive to the mass flow rate of gas. Mixing ratio is equal to mass flow rate of abrasive divided by mass heat of gas. Metal removal rate increases with increase of mixing ratio. Certain limit after it decreases gradually. Standoff distance, nozzle tip clearance. The distance between the nozzle tip and the workpiece has great influence on the diameter of the cut, its shape, size, and also on the rate of material removal. The material removal rate first increases with the increase of tip clearance from the workpiece upon up to a certain limit. After that, it remains unchanged for a certain tip clearance and decreases gradually. That means the material removal rate first increases with the increase of tip clearance from workpiece up to a certain limit. After that, it remains unchanged for a certain tip clearance and then decreases gradually. It would be noted that the metal removal rate keeps on increasing up to a nozzle tip clearance of 10 mm. After that, it decreases due to drag of atmosphere. Advantages of abrasive jet machining. The process is suitable for cutting all materials. Even diamond can be machined by using diamond as abrasive. There is no heat generation during this process, so thermal damage to the workpiece is avoided. Very thin and brittle materials can be cut without any risk of breaking. There is no direct contact between the tool and the workpiece. Low initial investment, good surface finish. It can be used to cut intricate hole shapes in hard and brittle materials. Disadvantages of AJM. Material removal rate is slow. Soft material cannot be machined. Soft material cannot be machined. Meshing accuracy is poor. Nozzle wear rate is high. The abrasive powder used in this process cannot be reused. There is always a danger of abrasive particles getting embedded in the workpiece. So, cleaning is essential after the operation. It requires some kind of dust collection system. Application of AJM. Where and all we are using this one? The process is widely for mixing of hard and brittle materials like quartz, ceramics, glass, sapphire, etc. Fine drilling and micro cutting. Mixing of semiconductors. Mixing of intricate profiles on hard and brittle materials. Cleaning and polishing of plastics, nylon, and Teflon components. Frosting of the interior surface of the glass tubes, surface etching and surface preparation. Characteristics of AJM: work material, hard and brittle materials like glass, quartz, ceramics, mica, etc. Abrasives: aluminum oxide, silicon carbide, glass powder, dolomite. Size of abrasive around 25 micron meter. Flow rate 2 to 20 gram per minute. Medium: nitrate or carbon dioxide or air. Nitrogen, carbon dioxide or air. Velocity 125 to 300 meters per second. Pressure 2 to 8 kg per centimeter square. Nozzle material: tungsten carbide or synthetic sapphire. Then we are going to water jet machine. Introduction. Water jet machine (WJM) process is an extension of abrasive jet machine process. In this process, high pressure and high velocity stream of water is used to cut the relatively soft and non-metallic materials like paper boards, wood, plastics, rubber, fiberglass, leather, etc. Principle. When the high velocity of water jet comes out of the nozzle and strikes the material, its kinetic is converted into pressure energy, including high stresses in the work material. When this induced stress exceeds the ultimate shear of the material, small chips of the material get loosened and the surface finish is exposed. This is a schematic drawing for water jet machine. Here water is pumping through the pipeline and it is directly coming to the surface on surface of the workpiece. And abrasive also is coming and mixing with that water and it is forcibly for fed on the surface of the material. Then there is a cutting action is abrasion is taking care for remove the material. Water jet machine construction. It consists of pump, accumulator, control valve, regulating chamber, nozzle, etc. A pump or intensifier is used to raise the pressure of water. Pressure normally used in the system are in the range of 1500 to 4000 Newton per millimeter square. Since the cutting action may not be continuous, the accumulator is used to store the water and also it helps in eliminating pulsation. Nozzle is used to increase the velocity of the water jet. The nozzle is made up of sintered diamond, tungsten carbide, or synthetic sapphire. The exit diameter of the nozzle is in the range of 0.05 to 0.35 millimeter, and the exit velocity of the water jet from the nozzle varies up to 920 meter per second. A regulating chamber is incorporated to control the flow of water. Working principle. The working principle of water jet machining is very similar to that of abrasive jet machining. A pump or intensifier is used to increase the pressure of water and the water passes onto a accumulator from the pump. Water under pressure from a hydraulic accumulator is passed through the orifice of a nozzle to increase its velocity. When the high velocity of water jet comes out of the nozzle and strikes the material, its kinetic energy is converted into pressure energy, including high stresses in the material. When this induced stress exceeds the ultimate shear stress of material, small chips of the material get loosened and a fresh surface is exposed. Process parameters. The following parameters are needed to utilize the water jet machining process successfully. Material removal rate, geometry and surface finish of material, water rate of the nozzle, wear rate of the nozzle. Material removal rate. In water jet machining process, material removal rate is directly proportional to the reactive force of the jet. That means MRR is directly proportional to F. MRR directly proportional to M into V. That means F equal to M into V, where M is the mass rate of flow, mass flow of rate, and V is jet velocity. Material removal rate. Mass flow rate depends on nozzle diameter and fluid pressure. Jet velocity depends on the fluid pressure. MRR is directly proportional to the diameter of the nozzle and pressure. Stand-off distance is the distance between the nozzle tip and the surface of the material being machined. When MRR increases, the stand-off distance also increases up to a certain limit. After that, it remains unchanged for a certain tip clearance, certain tip distances, and then falls gradually. Geometry and surface finish of work material. Geometry and surface finish of material mainly depends on the following parameters: nozzle design, jet velocity, cutting speed, depth of cut, and properties of material to be machined. Wear rate of the nozzle. Nozzle wear rate depends on the following factors: hardness of the nozzle material, pressure of the jet, velocity of the jet, and nozzle design. Advantages. In water jet machining processes, water is used as energy transfer medium. It is cheap, non-toxic, and easy to dispose. Low operating cost, low maintenance cost. The work area remains clean and dust-free. Very less amount of heat is generated during cutting operation, so there is no thermal damage to the work. Easily automated. Disadvantages. Initial cost of this process is high. It is difficult to machine hard materials. Noise operation. Applications. This process is very convenient for cutting relatively soft and non-metallic materials like paper boards, plastic, wood, rubber, leather, fiberglass, etc. It can be used to cut intricate contours. So water jet machining. This is schematic drawing for this abrasive water jet machine. This is abrasive water jet machine. This is the characteristics of water jet machine. Work material, soft and non-metallic materials like paper boards, wood, plastics, rubber, etc. Tool, water or water with additives. Additives, glycerin, polyethylene oxide. Pressure of water 100 to 1000 megapascals. Mass flow rate 8 liters per minute. Power 45 kilowatt. Metal removal rate 0.6 millimeter cube per second. Feed rate 1 to 4 mm per second. Nozzle material tungsten carbide or synthetic sapphire. Standoff distance 2 to 50 mm.